let's explore binary search trees. So it's very simple. In binary tree, we have no such condition. In binary search tree, right, there is one condition that the left subtree of the node contains only nodes less than the root node, and the right subtree contains the nodes greater than the root node. That is the condition in binary search tree. Okay, why this tree? Because the search operation is efficient compared to the binary tree. In binary tree, we have to search every element, every path, but here searching is very easy. If you are organizing the data in this pattern where the left subtree, all the elements in the left subtree of the root are less than the root, all the elements on the right subtree are greater than the root. So this we call it as binary search tree. Okay, so this is important because the search operation is less. Normally in binary trees it is worst case, that is order of n, whereas in binary search tree the worst case search operation is order of log n. Okay, so it is reducing a lot, that's why we are following this design of binary search tree. Okay, so how do you insert an element into binary search tree? Because you already have a tree in place. Let's say this is the tree what I have with me, 6. If you see, the left subtree is less than 6, the right subtree is greater than 6. Okay, so when you have a tree structure like this, if you want to insert a new element into the binary search tree, what you have to do? You have to insert the element where the element what I want to insert is 5. So where should I place this? I have to place it after 4 because it is less than 6, it is less than 6 and it is greater than 4. So it has to come here. So how do you insert it here? First you will check the number which you want to insert, k equal to 5. Is k greater than the root element or k less than the root element? Okay, so we have found it that k is less than root element. Therefore, you will shift your temporary node to here. This becomes your temp. Now again check whether k is greater than temp or k is less than temp. Accordingly, if it is less than temp, you will go to the left side. If it is greater than temp, you will go to the right side. So in this case, what is your logic? Temp equal to temp right. In this case, it is temp equal to temp left. So now what will happen here? Since it is 2, 5 is greater than this temporary element, that is 2, you have to temp equal to temp right. So this becomes our temp now. Okay, it has been shifted to this place now. Again check whether the element which you want to insert is greater than temp or less than temp. So it is greater than temp. When it is greater than temp, you will check here. So greater than temp means you have to go towards right side. What do we have in the right side? We have null. Okay, we have null here. When it is null on the right hand side, when we have a null element on the right hand side, then you have to insert that this new node will be inserted on the right hand side. Okay, so this is the logic. Again I will repeat quickly, we will see the code also. When you are inserting a new element into a binary search tree, you have to check whether the element which you are inserting is less than 6 or greater than 6. If it is less than 6, make your temporary node to left side. If it is greater, make this as your temporary. After coming here, yes, 5 which I want to insert is greater than 2, so I will go towards right side. Then it is also greater than 4, I will go towards right side. I found it as null. When the element is null, there you have to insert the new node. Okay, so this is the process of doing it. If you see, how do you insert an element? This is all the default structure what we create. Okay, so I am from the main, I am calling, I am inserting these elements. After that, I am trying to follow the pattern. So what is happening here? When you are inserting, this insert function is called. Okay, so if the root was null, we are returning this. Otherwise, you see the actual logic here. While current not equal to null, parent equal to current. Okay, parent equal to current. That's what temporary equal to current. Then if value which I am inserting is less than current data, temp data, then go towards left side. If the value which I am inserting is greater than temp data, go towards right side. Okay, now this is done. You will go next. If the value less than parent data, Okay, if the value is less than parent data, then parent left equal to new node. So we are making this, right, this becomes our parent node. Now if the value which I am inserting is, in this case it is greater, so parent right is equal to new node. Though this node we are already creating, node in the sense not circle, it is like this. Okay, this node already we are creating, and 4 will be something like this, no? So 4 will be like this, which will have null on both sides. Okay, so it has 2 on top, it has 2 like this. If I exactly draw, it is something like this. Okay, in this case, if the number which I am inserting, this is my parent node, this is my parent node. If the number which I am inserting is greater than this parent node, then the new node parent right equal to new node, means this is my new node 5 with both null. This link I am establishing. Okay, that's what we are doing it here, to establish the link between the new node. How to create new node? This one line is enough. Node star new node equal to new node value. Okay, so this will create the new node, and accordingly we are writing the logic here. Okay, so this is just to give an overview, because when we solve the problems we have to always, because binary search tree logic is comparing. Okay, comparing where I have to insert, where I have to delete, all that comes into BST. Okay, so logic is simple. I'll repeat once again what we are trying to do. Initially I have created a root null pointer, insert root equal to insert 50. So first element is inserted, then insert 30. So I am calling, see, again when I write insert 50, this function is executed, insert and 50. Root is null, so if root is null, return new node. So that is the only element in the tree, that is the only element in the tree. Okay, next again insert root 30. So is the root null? No. Then node current equal to root, this is my current. Node parent equal to null, I am taking another variable parent which is pointed to null. Then while current not equal to null, yes, is current null? No, there is some root element 50 is there. Now parent equal to current, make this as also the parent. Okay, now if value, what is the value which I am inserting here? 30. See, value is 30. If 30 is less than current data means 50, is 30 less than 50, then current equal to current left, then current equal to current left, move towards left side here. Okay, so my current is pointing to this node now, my current is pointing towards left side. Okay, next, if value is less than parent data, okay, if value is less than parent data, parent left equal to new node. So here I will get the 30, because parent is this, right? So value is less than parent data, then parent left equal to new node. I got this. Again go insert root 70. Okay, it will go here. Is the root node null? No. Current is root, this is my current. Then node parent null, parent will be initially null, while current not equal to null, yes, parent equal to current, this also became my parent. If value less than current data, is it less than 50, 70? No. Is it greater than? Yes, then current equal current right, which is already null, this is also null. So there is no change in this, nothing will happen because of this statement, because current right is null, we cannot go there. Now if the value is less than parent data, 70 is less than parent data, no, then parent right equal to new node. So for this node, right side the new node will come, that is 70. Okay, now let's again see, this is my current. Next insert 20, let's see how this 20 gets inserted here. Okay, I am calling insert root 20. So in this case root, this is not null, it will this is my current, parent is null, current not equal to null, yes, parent equal to current, this became my parent. Then if value less than current data, yes, what is my current data? 50. Okay, value is 20, it is less than 50. In this case current equal to current left, so I come back here. So this becomes my current now, this current is deleted, this becomes my current, 30 becomes my current. How long should I do this? I should repeat this until the current not equal to null. Until the current not equal to null. So it will stop here because it does not have any left and right, which both left and right are null. So it will stop here. Now, if value less than parent data, is the value less than parent data. Okay, so yeah, we made parent equal to current, right? Second iteration, this also will become my parent. Sorry, in the next iteration, this also become my parent. Now, if the value less than parent data, so 20 is less than 30, yes, then parent left equal to 20. Okay, so this way you can keep inserting the elements into the tree. I will make it clear, because trees, if you are looking for placement in good companies, you definitely have to solve problems on trees. You should be able to code problems. Okay, it is very, very important. You should know, you should execute the problems like anything, right? So coding is important. Linked list, you should explain the solution, whereas for trees you should be able to, it is not that only solution is enough for linked list, but for trees specially you should be able to do coding nicely. Okay, so I will insert 40 and then wind up this topic. So root 40. Okay, so root is not null, current equal to root, this is my current, I will just make it C. Then parent equal to null, parent is equal to null initially, while current not equal to null. Is current not equal to null? Yes, it is not null. Go inside. Parent equal to current, this becomes my parent. If value less than current data, value is 40, value is 40. Is 40 less than 50? Yes, then current equal to current left. So this becomes my current. Okay, next iteration, it will this, if condition is over, from here it again go back to while condition. Is current not equal to null? Yes, current is 30 is not null. Again, parent equal to current, this becomes my parent, parent also has gone. Now, if value less than current data, value is 40, is 40 less than 30? No, current is here at 30. Is it less than 30? No. In this case, go to else part, current equal to current right. Okay, current equal to current right. So my current from here will move to current right, which is null. So there will not be any change. So my current will be here only, and my parent also will be here only. Then next iteration will go, is current not equal to null? Yes, current became null. No, current equal current next means current became null because of this statement, current equal current right. For 30 there is no right side. For 30 there is no right side, it is null only. So my current is pointing here, which is null. In that case, stop this looping. Stop this looping. Your parent, where is your parent? Your parent is here at 30. Now you come here. If value is less than parent data, 40, is it less than 30? No. Else parent right, that is 30 right, is equal to new node. That new node with element 40 will come here. So in this fashion, you have to keep inserting elements into the tree. It is very important to know how to insert, delete and finding minimum, maximum into binary search tree. Okay, because that is basic. Without this you cannot solve any problem of binary search tree, right? So this is the logic for inserting an element into BST. Let's also see how do you delete an element into BST. Okay, please pay attention to understand how we delete the elements from the BST. Right. So this is my tree what I have with us, 6, 2, 1, 5, 8. We have to delete this 5. So in delete there are multiple cases. Okay, in delete there are total 3 cases, case 1, case 2 and case 3. Okay, so what is this 3 different cases? Case 1, you are deleting a leaf node 5, you want to delete a leaf node 5. Okay, that is one case, right? This is easy to delete because it is the independent tree. I have to just break this connection. You have to do searching. After searching, break that connection because it's a leaf node. Simple. Case 2, see, I am deleting a node 4 which has a left child 3. So when I am deleting this node 4, it has a left child. I should break this connection. If I break this, this also is lost. For that reason, I have to map this element to 2. I have to map this element to 2. That is the second case. See, node to be deleted has no children, leaf node. It is very simple. node to be deleted has one child, it is also little simple like this case. If you see this diagram here, I want to delete 4 which has one child. So you break this connection, form this connection, then break this connection. So the tree becomes 2, 1 here and 3 this side. 4 has gone. That is simple. But the third case, node to be deleted has 2 children. Node to be deleted has 2 children. This is a typical case. Let's say, suppose you are deleting, here. Suppose you are deleting 2. You want to delete this 2 from this. So it has 2 children, 1 and 5. So you have to tag them to some other nodes, right? So for that we have logic. Let's try to understand the logic, what we try to do when you are deleting an element from the binary search tree. Okay, see, first case 1, deleting a leaf node. So first thing you have to traverse, find out. Once you reach there, once you traverse and reach there, you just make, this will be your parent, this will be your current. Okay, iteration like we have seen in the previous problem. This will be your parent, this will be your current. Just make parent right equal to null. That's it. This is deleted. Okay, so see the logic here. Case 1, node to be deleted has no children, right? So if you will have your current here initially. Element what you want to delete is 5. Same logic of searching. Is 5 less than 6? Yes, make this as your current. Is 5 less than 2? No. Greater than 2? Yes, make this as your current. Okay, somehow you have reached here and your current became 5. Now, if current left and right both are nulls, okay, current left and right both are nulls, then if current is equal to root, this itself is the root element? No, root is here. So that is not the root element. Then if parent left equal to current, so this will be my parent, okay. So if parent left equal current, no, my current is 5, my parent is 2, 2's left is 1, then else parent right equal to null, simple, parent right equal to null. So you are just making it null. So this node is deleted. Okay, this connection is deleted. So this node becomes free. So 3 will become simply 6, 2, 1 and 8 like this. 5 will be deleted. Okay, suppose you want to delete 1. Let's say you want to delete 1. So the key element which you want to delete is 1. This is my root, this is my current, this is my parent. Okay, so is 1 less than current? Yes, make this as your current. Is 1 less than 2? Yes, make this as current. Accordingly, your parent will move one step ahead. So your parent will come here. This is my current. Is currents left and right both null? Yes. Then parents, is this current left to parent? Yes. In that case, make this as null. Okay, simple case what we are able to see it here, right? Now second case, this case, see, I want to delete 4, I want to delete this 4 which has one child. Okay, it has one child. So how can we do that, right? So in this case, what is the logic again here? See, I want to delete 4, the element which I want to delete is 4. Okay, now this is my current. Somehow you will reach here, with iteration you will reach here as current. This will be your parent. Parent is at 2, current is at 6, 4, right? Now you see the logic. If child left right both are null, current left equal to null, current right equal to null, no, right? It has some element 3, so we are not going here. Okay, because we wrote here, no, if this is null, here OR, you see it is OR symbol. Is any one of them null? Yes, the 4 right is null, the 4 right is null. So in this case, node star child, here you are having one condition. You are deciding the child, you are trying to identify the child, which one is the child element. Okay, so current left not equal to null. If current left is not equal to null, is the current left not equal to null? No, it is element is there. In that case, current left. In that case, current left. So this is mapped as your child. This is mapped as your child. Okay. Next. Sorry. child we have found out. Now what are the things what we have with us? 4 is our current, 2 is our parent, and this 3 is our child. This is our current that we have found out. If current equal to root, no, current is not root, it is root is something else. If parent left equal to current, no. Parent right equal to current, parent right, yes, parent left is not current, definitely it will be parent right. In that case, parent right equal to child. So parent right equal to child, this connection I am forming. So this connection I am breaking it. That's it. Okay, so we are trying to find out the parent, current and the child node. How am I finding child node? Once I reach to the current path, I am just checking whether current's left or current's right is null. Which one is there? Which one is not null? Is the left not null or the right not null? If left is not null, then make the child this as your child. Okay, if right is not null, then make it as child. Okay, so that is the logic we are following here. To delete a node which has at least a single children, its parent we are mapping it. Okay, how are we mapping? You see, this is the parent, this is the current, and this is the child. Okay, in this case, if parents left is the current, then parents right will be 3, or otherwise, if this is the current, if parents left is current, then parents right will be the child. Okay, that way we have to map it. Then the third case of deleting an element, how we delete that element? Node to be deleted has 2 children. So you have to first find out the minimum. What you have to do here is, actually when you are deleting 2, among these 2, which one is minimum or maximum? Any logic you can use. See, if I am deleting 2 means 5 will come here, this will become null, this will not be there, this will be our tree, that we know the solution, right? If a tree is like this, 6, 2, 1 and 5, this side 8, if I am deleting 2, in place of 2, which element should come? 5 should come, obviously, because this side should be less, 1 cannot come, right? So why? Because this side everything should be lesser than, it means 1 also can come, sorry, 1 also can come, I am sorry. So when you have 1 here and 5 here, if this is 2, right, you can put 1 here, you can put it 1 here, this also will work. So for that reason, find the minimum of current right. Okay, successor equal to find minimum of current right. Now once you find minimum, it's a separate function to find out the minimum element on the current right. So on the current right, this is my I will somehow reach that point, this is my current, find the minimum element on the current right, that is 5. Then successor data, successor value the same, delete node, root comma successor data, current data equal to successor value. So what we are trying to do here, see, you see this logic, I am trying to find out the successor, I am trying to find out how find minimum current right. How am I reaching to the current? Current is the element which I want to delete. Okay, so we are reaching the number 2 as the current. After that, that is my current right in this side. What is the minimum element? 5 itself is the successor. This is my successor. Next, successor value equal to successor data. Again, successor value SV equal to 5. Simple. Then delete node, I am calling a function delete node, root comma successor data. I am saying delete the node. So how are we deleting that? Parent null, current root, current data not equal to key. Key means the element which I want to delete that. So parent equal, if key less than current data, current left or current right. So in this case, this will simply, this is the thing, so it will make 5 as here and 1 as here, right? This delete node function will try to check the condition and see key less than current data is the successor value which I am trying to do that. Is it less than current data or not? If it is less than, current equal current left or current right. So it will delete that. Then current data equal to successor value. This I am placing it 5 here. So the tree will become 6, 5, 1 and 8. Okay. So, if since I am finding the minimum here, since I am finding the minimum, if you find maximum, you can change this to like this, 6 then 1, this side 5 and this side 8 is possible. Left hand side everything is less than 6, here also this side it is less, this side it is greater than that, here it is greater than that, you can satisfy it. So, there are two cases. So, when you are deleting an element in a binary search tree, you have three cases. Okay. Deleting child with deleting node with no children, with one child and two children. Okay. Now, finding an element in a binary search tree. How do you find for an element in a BST? Okay. So, it is simple. We have been doing this. This is the my root node. If the element which I am finding is some let us say 9, is it less than root? Yes, go this side. Here is my temporary or my current. Is it less than 6? No, it is greater than 6. Yeah, come this side, you can find it out. Very simple logic. See, while current not equal to null, if the current data equal to the key, this is my current. Is this 10 equal to key? No. Then, if key less than current data, yes. Is key less than current data? Yes, it is less than current. Then current equal to current left. So, this becomes my current. Again go. Is current null? No. Is that key which I am finding is less than current? No. Is greater than current? Yes. Make this as my current. Again check, is the key equal to current data? Yes. Then return true. So, we found the element. Simple logic. This is what we have been doing in all those logics. That is why binary search tree searching is very, very simple. Okay. Simply you are just comparing whether to go left side or to right side. Again left side or right side. Somewhere you will stop and find the element. After going that path, if you are not able to find, you can say element not found. Okay. So, I will just skip this recursion. We will go back to yeah. Now we will see. We will try to understand the problems. Let me share. Yeah. Some empty slide here. Yes. So, let us discuss questions one by one. How do you find out the minimum and maximum of a binary search tree? This is the first problem what we are trying to see. A previous question, not both, but only one question they might have asked. Find minimum and maximum element in binary search tree. Okay. So, let us say you have a tree like this, 6, 5, 1, not 3, 5, here 8 and here it is 9. Let us say this is what we have with us. Yes, this is the tree what I have with us, and we want to find out the minimum element of a binary search tree. It is very, very simple. How do you find out the minimum element? Why? Because the always in binary search tree, the minimum element, the least element is at the leftmost corner. Okay. And the maximum element is always at the rightmost corner. Simple base case we will see, then we will try to see the typical cases what we have with this BST. Okay. So, how do you find the minimum element? Travel to the leftmost side. Okay. So, this is my root, this is my root. So, what we try to do here, you will take a temporary pointer, okay, temporary you will take, then you will simply do until the temp left not equal to null. Until the temporary is left not equal to null, simply keep doing temp equal to temp left, temp equal to temp left. Okay. So, yeah, 6, is 6 left not equal to null? Yes, it is not equal to null. Go to 3, this becomes my temp. Is 3 is left not equal to null? Yes, this becomes my temp. Then is 1 is left not equal to null? It is null. Stop there, just print the temp data. That is the minimum element. Okay. Next, find out the maximum element. Same way, you traverse to the right, you will get the element. Okay. Where logic is simple again, while temp right not equal to null. Well, temp right not equal to null, temp equal to temp right. Keep going that way. Suppose 9 is not there here, no problem. Why? See, the 6 is my temp. Is temp right not equal to null? Yes. Then this becomes my temp. Is temp right not equal to null? It is null. It is null here. So stop. This is my temp. So the maximum element is 8 in the tree. Simple problem, finding minimum and maximum element in a binary search tree, which is the leftmost and the rightmost element. Okay. So the next one more previous question is identify whether two trees are identical or not. Identify whether two trees are identical or not. So what is this problem? See, I have a tree here, 1, 2, not a binary search tree, it's a normal tree. Same question was once asked for binary search tree also. Okay, so I have this 1, 2, 3 and here I have 4. This is tree 1 data with me, and I have another tree, same tree, same way I have it like this. There are two trees, right? We have to identify whether two trees are identical or not. So what you can do here to do that identical, right? So if R1, this is my temporary 1, this is my temporary 2. You have to compare if T1's data is equal to T2's data. Okay, if T1's data is equal to T2 data, right, then if this is equal, you have to go to the left side as well as right side, both the sides. If both the data are equal, then you have to check T1 left also, T1 right also. So for that we use recursion here. For that we use recursion because I have to call the same function at a time for two different nodes. Okay, I have to call the same function at a time for two different nodes. For that reason, what we try to do here, we will write a function, something, I will write is identical. I will be capturing the temp values node star T1 and node star T2. So what is my logic here? See, first I have to call for T1 data is equal to T2 data. This I should call, and if this is true, then again I have to call the same function is identical, right? What I have to do here, R1 left, T1 left comma T2 left. Okay, so these things are passed here. Again this data will be compared, and this also should be true, and is identical T1 right comma T2 right. So this way in recursion this will be passed, again checked, again this will be passed, again checked. So this way it will repeat, and it will say whether both the trees are identical or not. Here identical means having same elements. Okay, having same elements T1 and T2, whether everything is perfect or not, right? So it's very simple problem, but using recursion only you have to solve, because you have to compare just the data. This is common thing, this will be true, and is identical left and left, then right and right. Again left and left, right, there is nothing. So until that we have to keep repeating this process, whether two trees are identical or not. Okay, now one more third interesting problem what we have is finding the kth largest element. Kth largest element in binary search tree. So what is this problem? How do you find out the largest element in the binary search tree? Okay, so we have, suppose if I have a tree 20, this side some 8, this side some 22, then I have here 4, this side I have 12, and here I have 10, and here we have 14. Okay, so this is our tree. Now I have to find out the kth largest element. Let's take k equal to 3, which is the third largest element. So here see 22, 20 and 14, right? If you arrange them 22, 20 and 14. So 14 is the third largest element in this tree. So how do you find out the largest element. Largest of all the elements, it's very easy. Rightmost side, right skew tree. You go right side, right side, right side. The last element is the largest. But third largest, second largest, how do you find it out here? Okay, so just think of the solution, how we can find out the kth largest element. Can we use some other data structure? Can we use array to store them back and then find out, or in linked list, how can we do that? Because they are connected linked list. So is there any technique existing with which we can find out which element is the kth, or here in this case, if I take k equal to 3, or if you say, let's say k equal to 4, I want to find out the fourth largest element, let's say. So answer should be 12 here, right? 12 is the fourth largest element. So how do we find out that, right? Let's see the solution for this. How do we actually find out the kth largest element in a binary search tree? So the approach is, see, we have studied about traversals, and we know largest element is always on the right hand side. But in this case, from right I have to slowly come back towards this side. So we know about traversals, right? In order traversal means it is left, then root, then right. Pre-order means it is root, left and right. Post order means it is left, right and root. Okay, but here you have to apply a new technique or a new pattern among these, not from these three. What is that? You have to first do it right. You have to first do it right, then root and then left. Why? All largest elements are in the right side only. All the largest elements are in the right side only. So arrange them in that order. Why? First only the largest element is 22, then on top comes 20, then on top comes 14. This way it goes, right? So we know that the largest element are always on the right hand side. So traverse right first, then the root and then the left. Arrange those elements in that pattern. So in this case, let us first do the traversal. Right, root, left. You will get the solution, right? I have to first do right, then root and then left. Let's do this traversal. So right means this side, only one element is there, so 22 will come. Then next, since there is no children here, I will go back to the root, so 20 will come. Next, in the left hand side, this tree, again I have to take the rightmost tree, so this tree I have to take. In this again I have to take the right tree, so 14, then root, that is 12, then left, that is 10. So this is done now. This right is done now, right is done. After this, go to the root, 8, then go to the left, 4. That's it. We have traversed it. So once you follow this pattern of traversal, 22, 20, 14, 20, now this you can store it somewhere. You keep traversing, store them in some array or some stack, wherever you want to store, right? So they asked the fourth largest element. So the fourth element is the largest element. If they say k equal to 3, you want to find out the third largest element, 14 is the largest element. So while traversing, take that element, store it into the array, keep storing from index 0, 1, 2, 3, so on. Okay, if possible, you can take that, or if you, since array we do not know how much size to declare, you may take some stack also, no problem. You can take some stack. Okay, so once you do that stack, you can store them and you can pop out the elements and try to find out the topmost element. Okay, so that way, anyway, you can store them in an array or a stack data structure, and you can do that. Only things, that's what the clear idea here is, you to be perfect with traversals. Okay, for this to find out the largest element, the only technique is right, root, left, which we never learn it or do it for traversals. We only do left, root and right, or else left, right and root, or else it is right, left and right, root, left and right. So no chances that we are beginning with the right side first. So if you do to find out, now with this logic you should be able to tell me, you could also solve which is the kth smallest element. Kth smallest element, this one is enough. Left, root, right is enough. Traverse it in that way. So you will first do 4, there is nothing left and right, so left is done, then go for root, then go for right. In right, this is my right. In this, you first go for left, then go for root, then go for right. Now this full left is over, then go for the root and then 22. Simple. So in this, the third largest element is 10, third smallest is 10, or fourth smallest is 12. That way we can find out. Okay. So it's again the traversal techniques what we have seen, right? We have studied about different traversal techniques. I'll just show you how do we actually do the traversal. Yeah, we have seen how to do the level order traversal, also the other in order, pre-order and post-order traversals. The same logic we have to use it here to solve that problem of finding out what we say, the kth largest element in the tree, right? Kth smallest or kth largest of binary search tree. Okay, so there are so many such problems which are based on these concepts, right? So please practice problems on trees.